Let's take a look at another question on proofs in plane geometry from St. Margaret. The diagram shows the circle ABCD and the tangent ST to the circle at point C. Let's put this information in. We have tangent ST, which is this line over here. So if you notice that we do not have radius or diameter or center of circle, meaning I won't put 90 degree in, and keep in mind that high chance we are going to apply alternate segment theorem. Let's continue reading. The point B lies on AT such that AB equals to BT. Let's put that in as well. So I know this two are equal. And the point C lies on the line ST such that SC equals to CT. Let's put this in, which is this one, equals to this one over here. Now let's be a little bit sensitive right now because we are given two midpoints. B is a midpoint, C also a midpoint. So we can apply midpoint theorem where I know that this AS line is going to be parallel to BC line. Now let's take a look at what we need to prove. We need to prove that triangle ABC, I'm going to label the angle in. Angle A, B, and C is similar to triangle SDC. I'm going to label that as well. Angle S, D, and C. Now let's take a look at the picture over here. Thinking of angle 1, 2, and 3, which are the two angles that are easier to prove. Since I have the parallel line, let's just focus on that. I can apply. This is angle number 3. If I apply alternate angles, I'm going to go to this angle here, will be the same as angle number 3. And this angle here, if you take a look at opposite of this angle, is going to be the chord line of DC. This is a chord. And take a look at the chord and the tangent. That's going to be your angle number 3 in red. So let me start writing the first one here. I'm going to start by writing AS is parallel to BC. And the reason is because I'm applying midpoint theorem. I'm going to write a bit more because B and C are midpoints of AT and ST, respectively. And using alternate angle, now my next line here, I'm going to write angle, the green one, number 3, BCA, equal to the blue number 3, which is CAD. This one, we're going to use alternate angles because we know the parallel lines. So I'm going to write AS is parallel to BC. Next, I'm going to write this angle, CAD, is equal to angle number 3 in red, which is DCS. Using alternate segment theorem. And since these two angles equals to the same angle, therefore, angle BCA must be equals to angle DCS. This one, we are explaining angle number 3 that you see in the diagram. Now let's take a look at the remaining angle, number 1 and number 2, which are easier to prove. If I take a look at the diagram, I'll be using angle number 2. So if you take a look at angle number 2 in red here, if I'm going to let angle number 2 be theta, this angle over here next to it is going to be 180 minus theta because they're on a straight line. And if you take a look at opposite of this 180 degree minus theta, you will see green color angle number 2. So this one here, they are going to add to 180 as well because you can see ABCD is a cyclic quadrilateral. So let me write my explanation over here. The next part here, I'll be using angle ABC, adding this angle with the opposite angle, which is angle ADC, will give me 180. This is using the concept of cyclic quadrilateral, but my explanation here will be angles in the opposite segment. Next, let me take a look at the other two. So I have this angle in red, number 2, STC, adding with angle, the same here, ADC, will be equal to 180. These are adjacent angles on the straight line. And since these two angles, adding with the same angle and gives you 180, therefore, these two angles must be the same. Let me write it down. Angle ABC must be equal to angle STC. And this one, we have proved that the angle number 2 in green and red, they are the same. And therefore, let me make a conclusion here. We have triangle ABC similar to triangle SDC using the concept of AA, angle, and angle. That's all for this question here.